Okay, so here we see how pressure is affected by depth, density, and gravity. So first, with depth, we're using this pressure gauge. We see here at the top of the water, the pressure is 102.9, roughly around there, 101 kilopascals. As we go deeper in depth, the pressure increases. This is also at Earth's gravity with atmospheric pressure present. And as we go down in depth with everything else set to normal, the pressure increases to 129 kilopascals just because of the depth. If we do the same thing and we change the density of the water and we make it something more viscous like honey, we see already the pressure is increased at the top layer from 101 to 103, and as we continue to go down we see it increasing and increasing, although by the time we get to the bottom it is at a much higher pressure than just the water because of the more dense liquid that is above the pressure gauge and acting on it. If we were to convert it to a less viscous liquid such as gasoline, which is a thin, we see it as 120 kilopascals instead of 129 because it's a thinner and less dense liquid acting on the pressure gauge. In terms of gravity, if we just place this pressure gauge in the middle and return the viscosity to water and the density to water, and we adjust the gravity, if we lower the gravity, we see the pressure going down because the atmospheric pressure and the pull of everything towards the center of the Earth has been lowered. Therefore, the force acting upon this throughout everything, not just the water above it, but also the atmospheric pressure, is lowered. And if we raise the gravitational pull, we see a huge increase in the amount of pressure occurring throughout the whole body of water, no matter the depth and, in fact, the atmosphere itself outside of the water. Okay, so here we're taking a look at gauge and absolute pressures with regard to atmospheric pressure. Gauge pressure is a measurement taken against the zero at the standard atmospheric pressure. Therefore, in order to find the gauge pressure, one must take the pressure and subtract the atmospheric pressure which is added on. And here we see the atmospheric pressure as being 101.3 kilopascals. Now if we were to remove the atmosphere from this PhET lab, this operation, we would be able to examine absolute pressure. Absolute pressure is taken when the zero is taken from a vacuum. So here we see the pressure taken against that pressure in a vacuum, so 0 kilopascals. And when we put a pressure gauge in something like water without the atmospheric pressure, we do see just the pressure of that substance acting on that gauge and not the pressure of the atmosphere. So if we were to increase fluid density here, or if we were to increase the gravity acting upon this substance and this gauge, we do see an increase, and that is without the atmosphere. Now you can see if we turn the atmosphere back on, it goes up to 218, and that is no longer the absolute pressure because that is including the atmosphere in the gauge measurement. Here we're taking a look at the theory, the continuity equation, which states that if you take the height, or the cross section of one end of a pipe, so for example here we've got 1.2 meters, and you multiply that by the velocity at that point, which is 4.2 meters per second, that should equal the height of the other end of the pipe here, which is 2 meters, times the velocity, which is 1.6. However, here I had a little bit of an issue because when you multiply those two numbers together, or those four I should say, you actually end up with 3.2 and 5.04, which are obviously not equal to each other. So here I do not see the continuity equation present, which should mean that there is some sort of backflow or holdup occurring, which if we unpause this we don't see. So I'm not entirely sure as to why that's happened, but given the factors and the numbers that I have plugged in here, it hasn't seemed to work. Maybe that's because in this situation the water is being forced through, like in a generator where water can go upstream, up a hill, but I'm just not sure. Okay, well here we're taking a look at Bernoulli's principle. Bernoulli's principle, which states that if the pressure of a flow is decreased, the velocity will increase. And here we see the initial pressure starting here with about 120 kilopascals, and we've got the speed at 0.8 meters per second. And then as we go here and the pipe gets thinner and thinner, the pressure actually goes down to 102 kilopascals, and the speed increases dramatically from 0.8 to 6 meters per second, more than 6 times the speed we see here with a decrease in pressure. So we're clearly seeing a decrease, proving Bernoulli's principle. And part of the reason why this is taking place is because we have all this water here that's very dense, and over here, although the space is tightening and although the actual location through which the water has to pass is smaller, it is moving at such a quick rate that the volume and that water is actually able to escape that area, and so the pressure doesn't build. And it's just a very quick transition from around here to here. It just goes by very, very quickly, which we're seeing.